Hello. Throughout human history, we have been captivated by a single, profound question. What am I going to eat later? No, I joke, that is not the question. Although, it is still a pretty important one, and we will be meeting our hungry caveman again later. The question is, what is the universe made of, and how does it work, at its most fundamental level? Thousands of years ago, philosophers speculated that everything was composed of indivisible units, called atoms. Today, we know that even those atoms are made of smaller particles, so tiny, they almost defy the imagination. To give you an idea of exactly how tiny these are, the proton, one of the main particles that we are going to discuss a little later, is approximately 50 billion times smaller than the width of a human hair. To explore these subatomic realms, we need a machine that can investigate the properties of particles, a particle detector. And there is perhaps no better example than the Atlas detector at CERN. The sheer scale of Atlas is breathtaking. It is the largest particle detector ever constructed, and is one of the four main experiments at CERN's Large Hadron Collider. Measuring a staggering 46 meters in length, and 25 meters in diameter, Atlas is roughly the size of a 6-story building, and weighs as much as the Eiffel Tower. This engineering marvel is buried 100 meters underground, near the French-Swiss border, sitting at the heart of the Large Hadron Collider, LHC, the most powerful particle accelerator in the world. At the LHC, our friends the protons are accelerated to nearly the speed of light before colliding head-on in the center of the detector. These collisions create an explosion of subatomic particles, some of which exist for only a fraction of a second, before decaying into other particles. The challenge for Atlas is to track and identify each individual particle, amidst the chaos of the collision event. But why do we need such a colossal machine, to study the smallest particles in existence? The answer lies in the complexity of the particle interactions that Atlas observes. Let's begin with recapping what we have already found out about the universe, in terms of fundamental particles, from experiments such as Atlas, so far. The behavior of the fundamental particles is described by the Standard Model of Particle Physics, SM for short. In the SM, particles are divided into two categories, matter particles, known as fermions, and force-carrying particles called bosons, which dictate how the fermions interact with each other. Fermions are further divided into quarks and leptons, and are arranged in three groups called generations, depending on the mass of the particle. So, as shown on the slide, on the left-hand side of the diagram, the first generation consists of the up quark, down quark, electron, and electron neutrino. Some of these particles you may be familiar with. Protons, which can be found in the nuclei of atoms, along with neutrons, are comprised of up and down quarks. The nuclei of atoms are orbited by electrons, which play an essential role in many physical phenomena, such as electricity, magnetism, and chemical bonds. The bosons of the SM mediate the fundamental forces that act on the fermions, photons for the electromagnetic force, W bosons, and Z bosons for the weak force, and gluons for the strong force. Gluons are, of course, not to be confused with the warlike, humanoid, alien species from Star Trek. The electromagnetic force governs the interactions between electrically charged particles, and is responsible for all electromagnetic radiation. Meanwhile, the weak force can transform one lepton or quark into another, provided it is in the same generation. This is the force responsible for radioactive decay. The strong force is responsible for transformations between different quarks, and is the force that holds protons and neutrons together. The Standard Model has even been visualized as soft toys, with a different form for each of the particles, so you can collect your favorites. We are honored to be joined today by the top quark, which Eleanor is holding up. I like to invite him along when I give public lectures, because I spent most of my PhD research concerned with studying his properties, to search for evidence of, as yet, undiscovered particles, so we are used to working together. There is also the fact that, being the member of the Standard Model, that decays into other particles, in the quickest time, he struggles to get a date on a Saturday night. I feel a bit bad for the poor guy. But in all seriousness, the top quark has an important role in the world of particle physics, because of how much its behavior can tell us about another particle that's even more famous, the Higgs boson. Some of you might have heard of the Higgs boson, and for good reason. Even though its existence was predicted in 1964, until its discovery in 2012, this elusive particle was the missing piece of the SM. The Higgs boson developed its reputation as a celebrity particle, because its detection was greatly anticipated throughout the particle physics community, to verify that the SM was an accurate model of particle physics. Finding the Higgs was crucial, because it provides the mechanism that gives mass to all the other particles in the universe, whether they like it or not. Picture a universe where particles could zip around without mass. It would be chaos, and we'd have no planets, stars, or life as we know it. By the summer of 2012, all the particles predicted by the Standard Model had been observed. After years of searching and expectation, data from CERN's two largest experiments, ATLAS and CMS, began to show promising signs that the Higgs was within reach. Yet, despite the growing excitement, no official confirmation had been made. That is, until whispers began to spread across the scientific community, an announcement was coming. The date was set, the 4th of July 2012. Imagine the scene, hundreds of scientists, engineers, and students, all buzzing with excitement for a discovery, decades in the making. On the night before, eager students began queuing outside CERN's main auditorium, some even camping out by the doors, in hopes of securing one of the few coveted seats for the upcoming seminar. Everyone knew that something monumental was about to happen. On the morning of the 4th of July, CERN's usually quiet atmosphere was alive with energy and anticipation. The queues stretched around corners, winding through CERN's corridors, and spilling into overflow rooms. Those who couldn't find a place in the main auditorium packed into nearby conference rooms to watch the proceedings broadcast live. The excitement wasn't confined to the grounds of CERN either. Hundreds of thousands of people worldwide tuned in online to witness what promised to be a defining moment in the history of particle physics. Then, it happened. The Higgs boson was jointly announced by the ATLAS and CMS collaborations to have a mass of 125 GeV. This discovery was not just a triumph for the teams involved, but for the entire scientific community. It confirmed an essential piece of our understanding of the universe, cementing the Standard Model's predictive power. But have you ever wondered, how did these detectors enable physicists to finally detect the elusive Higgs boson that made headlines around the world? In fact, how do physicists see particles at all? How can ATLAS determine the mass of particles that are far too small to be measured on any scale, as well as investigating all other properties of particles? Particle detectors, like ATLAS, serve as the telescopes of particle physics, revealing the hidden worlds inside the atom, much like how telescopes help us study distant stars and galaxies. Tonight, we will journey through the anatomy of the ATLAS detector, to understand how it allows us to probe the properties of fundamental particles. We'll explore how each part of the detector plays a crucial role in capturing the fleeting evidence of particles created in high-energy collisions. At the heart of the ATLAS detector is the beam pipe, a vacuum-sealed tube that serves as the pathway for protons, traveling at nearly the speed of light. Inside the LHC, protons are accelerated around the ring, using a series of interconnected linear and circular accelerators. Trillions of protons circle the collider's 27-kilometer tunnel, 11,245 times per second. Once they reach the maximum speed that one part of the accelerator chain can achieve, they are shot into the next, until they collide with enormous energy, at the very center of the ATLAS detector. Their trajectories around the circular accelerators are controlled by very powerful magnets, asserting the electromagnetic force on the protons. Without any other force involved, the momentum of the protons would carry them in a straight line. These collisions unleash a burst of energy, creating a cascade of new particles. It is these particles that ATLAS is designed to measure every detail about, so that we can uncover the secrets of the universe. Let's explore how the bending of charged particles by magnets works in practice. For demonstration purposes, let's imagine these tennis balls represent the protons in the LHC. And here our ramp provides acceleration via gravity, which at the LHC would be our linear accelerator. At the end of the ramp, we have the circular accelerator, or our big magnet. Ordinarily, when we roll a regular tennis ball near a magnet, we don't expect it to change direction, otherwise, things would get quite chaotic at Wimbledon. However, some of our tennis balls contain magnets inside, representing our charged particles, protons, in the LHC. When Ellen repeats the experiment with one of these magnetized balls, we observe that the magnet alters its path, much like protons are guided by the magnets in the circular accelerators at the LHC, as they zip through the beam pipe. ATLAS also has its own magnets, to control the trajectories of the particles that are spewed out from the collision point when protons collide at high energies, so that it can detect them. There are two shapes of magnets in ATLAS, each with a specific purpose. The first is a solenoid magnet, a large cylindrical coil that wraps around the collision point at the core of the experiment, encompassing the component of ATLAS that is closest to the beam pipe, the inner detector. This subdetector keeps track of the paths that the particles created in the collision take. The solenoid magnet bends the paths of charged particles, as we saw in the demonstration, allowing us to measure their momentum as they travel away from the collision. This is due to the fact that there is a direct relationship between the strength of the magnetic field, the momentum of the particle in the magnetic field, and the radius of the path made by the particle. By analyzing how much the path bends, the momentum of the particles can be calculated. ATLAS also has a series of donut-shaped magnets, known as toroids, located in the outer regions of the detector, as shown on the slide, which are used specifically for tracking the behavior of muons. Muons are the cousins of the electron, but 200 times heavier, and one of their defining traits is their ability to pass through most materials with ease. Because of this, they can escape from the central parts of the detector without leaving a signature or detectable path, requiring a specially designed system to measure them. That's where the muon spectrometers, positioned around the outer circumference of Atlas, come in. These detectors are specifically tailored to capture and measure the properties of muons. We'll get to the muon spectrometer soon enough, but first, let's take a look at the detectors located nearest to the beam line, the ones that receive the particles from the collision first. This diagram shows a cross-section of the detector and the paths that particles take as they travel through it. When a charged particle, such as an electron or muon, passes through the inner detector, the magnetic field forces it to bend either to the right or left, depending on its charge. Negatively charged particles, like electrons and muons, curve to the right, while positively charged particles, like protons, bend to the left. But not all particles behave this way. Photons and neutrinos, for example, have no electric charge, so they pass straight through the detector without being affected by the magnetic field. This lack of bending helps the inner detector distinguish between neutral and charged particles. I must admit, I have a soft spot for the inner detector, as part of my PhD focused on devising a technique to use it to measure the intensity of the proton beam that passes through Atlas. The inner detector is composed of several subdetectors: the pixel detector, the semiconductor tracker, and the transition radiation tracker. The pixel detector, located closest to the collision point, is an array of highly sensitive silicon detectors, forming the first layer in Atlas's particle tracking system. It consists of 4 layers of silicon pixels, with each individual pixel smaller than a grain of sand. As charged particles shoot out from the collision point, they leave behind small energy deposits in the pixel detector. Each of its millions of tiny sensors acts like a pixel in a camera, capturing the precise location where a particle passed through. The result is a highly detailed image of the collision, with a resolution as fine as 10 microns, much smaller than the width of a human hair. This remarkable precision is essential for tracking particles, especially those that decay almost instantly after the collision. Like all detectors at the LHC, the pixel detector undergoes regular maintenance and upgrades to ensure it can provide the best possible particle tracking. These maintenance periods are crucial because, despite being designed to withstand high radiation environments, the intense energy from repeated collisions eventually causes wear and tear on the detector systems. During one of these scheduled breaks, when protons are no longer accelerated through the beam pipe, the innermost of the 4 layers of silicon pixels, called the insertable B layer, was added as an extra layer, just 3.3 centimeters from the collision point. This upgrade greatly improved the precision of particle tracking for particles that decay soon after the collision, especially particles that contain a bottom, or B quark, hence the name. The insertable B layer boosts Atlas's capability to pinpoint particle trajectories with even greater accuracy, helping to enhance the detector's overall performance. Next, the semiconductor tracker adds an additional layer of detection. With its 6 million microstrips of silicon sensors, the semiconductor tracker continues tracking particles as they move further away from the collision point. These microstrip sensors can be thought of as a tiny wire that picks up a signal when a charged particle interacts with the silicon, allowing the detector to record the exact location where the particle passed through. By combining the signals from multiple strips, the detector can reconstruct the particle's path with high precision. This is the part of the inner detector that I focused on in my own research. I developed a technique using the particle tracks, recorded by the semiconductor tracker, to measure the intensity of the proton beam that the LHC delivers to ATLAS. The number of particle tracks captured by the semiconductor tracker is directly proportional to the number of protons in the beam. Particle physicists refer to the proton intensity as the luminosity of the experiment. It is a very important measurement, as it tells us how many protons per second are entering the collision, so its accuracy underpins the success of all other measurements. ATLAS uses a variety of techniques to monitor the number of protons it receives from the LHC, both by using dedicated luminosity recording devices situated along the beam pipe, and by using data from other parts of the detector, such as the semiconductor tracker. It's a little like reading multiple books on a subject. By gathering data from different sources, we get a much clearer and more reliable understanding of what's really happening in the proton beam. The diagram refers to barrels and end caps, for example, the semiconductor tracker end cap. This is a bit of CERN jargon. The barrel region of ATLAS refers to the cylindrical part of the detector in the middle that particles would reach if they traveled approximately perpendicular to the beam pipe running through the middle of ATLAS. Think of it as the main body of the detector that wraps around the beam pipe. On the other hand, the end caps refer to the regions on either side of the detector. These areas capture particles traveling at a more acute angle to the beam pipe. You can think of the end caps as the bookends of the detector, ensuring that even particles moving at shallow angles are detected and analyzed. Finally, the transition radiation tracker serves as the outermost layer of the inner detector. Its unique design uses 300,000 gas-filled tubes, called straws, each just 4 mm in diameter, with a very thin gold-plated tungsten wire running through the center. The gas is a mixture of xenon, carbon dioxide, and oxygen. The way the TRT records the paths of charged particles can be visualized using the array that Eleanor is holding up. Each gas-filled straw in the TRT is represented by one of the yellow circles in the model. Charged particles crossing through the straws ionize the gas inside them, knocking electrons free and creating an electric current, represented here by the circle lighting up. This current is conducted away by the tungsten wire in the center of the straw. The detector then registers which of the wires inside the straws detected the current, allowing us to reconstruct the particle's path through the detector. It's like a trail of breadcrumbs that shows exactly where the particle went, making it possible to accurately track its trajectory. From these signals, we can not only reconstruct the path of the particle, but also deduce the type of particle it was. Continuing outward from the collision point, we arrive at the calorimeters. In the context of particle physics, a calorimeter is designed to capture the energy of particles, and hence record it, and its direction of travel. This is achieved by measuring the particle cascades created when high-energy particles interact with the material of the calorimeter, to induce electromagnetic or hadronic showers, the latter of which contains particles like quarks, protons, and neutrons. The diagram shows what would happen in a shower if the incoming particle was an electron, labeled E-. On reaching the electronic calorimeter, the electron loses energy, a photon, denoted by the Greek symbol gamma. The photon continues its journey through the calorimeter and subsequently decays into another electron and its antiparticle, a positron. Meanwhile, the electron in the top part of the diagram repeats the process of losing more energy as another photon. This process repeats itself to create the electronic shower until all of the particles have lost all their energy to the detector. These showers are converted into electrical signals to allow ATLAS to deduce the properties of the original particle. As the cross-section of ATLAS shows, the first calorimeter that particles encounter after passing the inner detector is the electromagnetic calorimeter, followed by the hadronic calorimeter. The electromagnetic calorimeter is made up of alternating layers of absorbing, high-density metal, either tungsten, copper or lead, that absorb incoming particles, converting them into a shower of new, lower-energy particles. These particles ionize layers of liquid argon, which are sandwiched between the layers of metal, producing an electric current that is measured. To keep the argon in liquid form, the electromagnetic calorimeter is kept at -184 degrees Celsius. Particles like protons and neutrons, that do not deposit all of their energy in the electromagnetic calorimeter, then meet the hadronic calorimeter, which is designed to capture the energy of hadrons, particles made of quarks. The hadronic calorimeter absorbs and measures the energy of these particles as they collide with atomic nuclei within the detector. The hadronic calorimeter in ATLAS is made up of alternating layers of steel and plastic scintillating tiles. A scintillator is a material that, when a particle passes through, the molecules within it are excited, that is, given additional energy. Then, as those molecules decay back to their original energy, they emit light, typically in the ultraviolet range. As particles hit the layers of metal in the hadronic calorimeter, they generate a cascade of new particles. The scintillating plastic tiles then convert this particle shower into photons, which are subsequently transformed into an electric signal. The strength of this signal is directly proportional to the energy of the original particle. This is similar to how we saw a shower from an electron build up. This allows the hadronic calorimeter to measure the energy deposited by hadrons with great precision. The tile calorimeter, a major component of the hadronic calorimeter, is made up of approximately 420,000 plastic scintillator tiles. This system forms the heaviest part of the ATLAS detector, weighing almost 2,900 tons. So, the inner detector and the calorimeters are busy collecting incredibly detailed information about every single particle collision in ATLAS. But here's the question, with all of these billions of collisions, how does ATLAS make sense of it all? To give you an idea of the scale, the combined data from these collisions has a volume of more than 60 million megabytes per second, the equivalent of 5,400 simultaneous streams of high-quality video. And while that's impressive, only a tiny fraction of these collisions contain something truly interesting that might lead us to new discoveries. Take MaIone research, for example. When looking for evidence of non-standard model particles, we expect that these new and exotic interactions are going to be incredibly rare, and their signatures may only be subtly different from the predictions of the standard model. Hence, when the Large Hadron Collider is running, more than 1 exabyte, 1,000 petabytes of data from particle interactions is produced each year. To put that into perspective, recording 1 exabyte of data would require starting a video call 237,823 years ago, around the time modern Homo sapiens first appeared. That's equivalent to our friend, the very hungry caveman, trying to get us to make an order on Deliveroo. Now, I know some of my friends like to waffle on, but even that is pushing it. The image on the slide shows a simulated collision. As you can see, each proton-proton collision causes many events, such as particles being created and particles decaying. Figuring out which events to keep and which to ignore is the job of the ATLAS trigger system. This system is designed to reduce the overwhelming data flow to manageable levels, selecting only the events with distinguishing features that are likely to contain something interesting for further analysis. The Atlas trigger system works in two stages. The first level trigger is a hardware-based system, built from custom electronics integrated into the detector itself. The trigger can evaluate whether an event is worth saving in just 2.5 microseconds, using information from both the calorimeters and the muon spectrometer. During this extremely short time frame, the data is kept in storage buffers, and if the event looks promising, it's sent to the second level trigger. The second level trigger is where things get even more interesting. This software-based system operates on a huge farm of around 40,000 CPU cores and has 200 microseconds to perform a much more detailed analysis of each collision event. Finally, the second level trigger selects about 1,000 events per second to save for further offline analysis. This selection is crucial because interactions involving new particles are extremely rare, and we need to ensure that the events we keep for analysis are the ones that have the potential to lead to discoveries. It's all about finding that one needle in a haystack of billions of particle collisions, and the trigger system is what makes that possible. Returning to discussing the motions of particles through the detector that create this vast quantity of data, it's important to note that not all particles are stopped by the calorimeters. The particles that escape are mainly muons and neutrinos. Neutrinos interact so weakly with matter that they pass through the detector almost unregistered. Meanwhile, muons, though more interacting than neutrinos, are particularly good at penetrating the majority of the detector material. Their momentum is eventually measured and recorded at the outer edge of the Atlas detector, where the muon spectrometer operates. The muon spectrometer is designed to track those runaway muons with incredible precision. Since muons are charged particles, their paths are bent by the powerful magnetic fields generated by the donut-shaped toroid magnets surrounding them. As we have seen with other charged particles, by analyzing the degree of this bending, the muon spectrometer can calculate the momentum of each muon. One of the technologies developed for Atlas to accomplish the precise measurement of muons is a device called a monitored drift tube, composed of 3 cm wide aluminium tubes filled with a mixture of argon and carbon dioxide gas. There are over 380,000 aluminium tubes stacked in multiple layers, providing a detailed and precise trajectory of each muon as it passes through the detector. Monitored drift tubes are used in the barrel region of the muon spectrometer, and are located between and around the 8 coils of the superconducting barrel toroid magnet. The muon spectrometer, like other subdetectors in Atlas, also underwent upgrades during the last shutdown. Prior to the upgrades, the end cap regions of the muon spectrometer were increasingly unable to distinguish real muons from other particles due to background noise, as the luminosity of the collisions has increased since the detector started operating. This is so that more particle collisions can be produced every second, hence increasing our chances of observing a rare event. To address this, the innermost part of the muon spectrometer's end cap system was upgraded. The original components were replaced by a new set of detectors, called the new small wheels, which offer faster and more precise tracking to help differentiate real muons from background particles. One of the main technologies that the new small wheels use is small strip-thin gap chambers, consisting of parallel 50 micrometer wires in a gas mixture. When muons pass through these chambers, as with the monitored drift tubes, they knock electrons out of the gas, and these freed electrons drift toward a wire at the tube's center, generating a signal, indicating the presence of a muon. These precision detectors can pinpoint the position of a muon to within a tenth of a millimeter, which is critical for accurate particle identification and momentum measurement. To ensure that only data relating to muons is recorded, the muon spectrometer has its own trigger system, designed to capture the data recorded on muons quickly. This trigger system can deliver information on muon tracks within just a few tens of nanoseconds after the muon has passed through the detector, ensuring that the data from high-energy collisions is captured and processed efficiently. The creation of the many bespoke components within ATLAS demonstrates the huge amount of research and development that is required to construct and operate such a sophisticated particle detector. This R&D also drives advances in other fields, such as medical physics. For example, inspired by ATLAS technology, a team has created an advanced multi-electrode array that can simultaneously record the neural activity of hundreds of retinal output cells in the eyes. Researchers are now applying this technology to retinal prosthesis studies. To give another example, technology developed by ATLAS engineers is being applied to detect gas leaks using ultrasonic pulses. Researchers are now looking to potentially use such technology in the control of the composition of anesthetic gases, such as xenon and oxygen, in real time, a mixing procedure which usually requires two separate analysis techniques. So, we have followed the paths of standard model particles through the layers of the ATLAS detector to understand how this unique machine helps us probe the universe at its most fundamental level. Now, we've come to the outer edge of the detector. But there is still one particle left, the neutrino. After all the layers, the beam pipe, the tracking systems, the energy-absorbing calorimeters, and even the muon spectrometer, neutrinos are the only particles that manage to escape detection entirely. Unlike other particles, neutrinos are almost impossible to capture, because they barely interact with anything. In the standard model, neutrinos are unique, because they don't interact through the electromagnetic force or the strong nuclear force, the forces that make it possible to detect most other particles. Instead, neutrinos only interact through the weak nuclear force, which means that as they pass through the detector, they don't leave any trace behind. They slip through the entire experiment as if nothing were there, completely unaffected by the materials and magnetic fields that capture and measure other particles. Because of this, we can't directly see neutrinos in the detector. Instead, we infer their presence by looking at what's missing. When the energy, or momentum, from a collision doesn't quite add up, it's often because a neutrino has escaped without leaving a trace. By deducing the neutrino's presence in this way, ATLAS allows us to study all the particle interactions in the standard model in incredible detail. Of course, understanding the standard model is only the beginning. The SM provides us with a remarkably coherent description of the known particles in the universe, and with the discovery of the Higgs boson, we have measured every particle it predicts. So, you might wonder, is particle physics now just about fine-tuning our measurements and comparing them with theory? Absolutely not. The reality is that the standard model, despite its successes, does not give us a complete picture of the universe. It can only explain the particle content of about 4% of the universe, leaving 96% unaccounted for. We know this because the observed rotational velocities of galaxies suggest that their total mass far exceeds what can be explained by visible matter alone. This missing mass, called dark matter, is thought to make up around 23% of the universe's energy-matter density, but the standard model does not include a dark matter particle. Then there's the even bigger puzzle of dark energy, which makes up about 72% of the universe. The unexpected discovery that the universe's expansion is accelerating, instead of slowing down due to gravitational attraction, points to an unknown force acting against gravity on a cosmic scale, which physicists labeled dark energy. The Standard Model does not provide an explanation of what could be causing this force. One of the main goals of ATLAS, and the other experiments at the Large Hadron Collider, is to extend our understanding beyond the Standard Model and address some of the universe's most profound mysteries. After the years of effort that international teams of scientists have put into designing and operating such sophisticated experiments, some people might see these unanswered questions as reasons to lose hope of ever fully understanding the building blocks of the cosmos. However, I look at it from another perspective. These unanswered questions are precisely what makes this the most exciting time to be working in fundamental physics. We have so much left to discover, and the possibility of expanding our understanding is thrilling. If I do sometimes feel daunted by how much we still have yet to understand about the universe, I like to think of one of my favorite quotes, written by Benjamin Franklin: "We are, I think, on the right road of improvement, for we are making experiments." Our experiments at the LHC are on the road towards discovery, pushing the boundaries of what we know about the universe. After all, the point of science, I think, is to provide a dependable method to explore the unknown. Thank you for listening.